So for today's physics club, we're extremely happy to have Professor Ben Nachman from Lawrence Berkeley Laboratory. So Ben is one of the early pioneers in using machine learning techniques for analyzing fundamental physics, in particular colliders such as the Large Hadron Collider. And so he's developed a lot of the techniques which are used by a lot of the students and postdocs here. So it's very fun to have him visit. And so for this work, he's received a bunch of awards, including the Experimental Physics Prize from the European Physical Society and the Wu Ki Tung Award for Research in QCD. And so today we're very happy to have him telling us about machine learning for fundamental physics. So take it away.
Great, thank you so much for the opportunity to be here today. And it's amazing to see so many of you in person. And I hope in the back you can hear me if I talk like this with my mask on. Is that okay? Thumbs up, excellent, very much, thank you very much. Okay, so I want to start by making sure everyone's on the same page and telling you what I mean by fundamental physics. So I'm going to cast kind of a wide net here, although my focus will be, as Ian said, anchored in collider physics. So I probably don't have to tell you that there are a number of core theoretical and experimental questions that have compelled us to explore fundamental structure. For instance, the Higgs boson. Here's a picture that probably many of you have seen with the quarks and the leptons, the force-carrying particles, and the Higgs boson neatly set right in the middle. It's exactly where we thought it should be, but also we don't exactly know why it should be there. There are other interesting theoretical questions, like why do neutrons have a net dipole moment? So if you just search neutrons on Google, you probably see pictures that look like this. But of course, in reality, the dipole moment is almost zero. And there are a number of other interesting questions related to QCD, its fundamental and emergent properties. On the experimental side, we know dark matter exists. Here's a picture of the bullet cluster. And we don't understand what is the particle nature of dark matter. Maybe it's not even particles. There are also questions related to flavor. So why do neutrinos have mass? Why are there different lepton flavors? Where did all the antiparticles go? And all these questions together motivate a deep exploration across many different areas. So to attack these problems, we've developed a number of large experimental programs in order to probe one or more of these deep questions. Here you can see pictures of a variety of these instruments for across fundamental physics areas. To match these experimental devices, we also have developed tools, computational tools, in order to couple these, to extract the most information from these experimental devices. And altogether, this is what I call the hyper challenge. Hyper in the sense that we have hyperspectral data. So these detectors have many, many channels, often multiple components. So you can think of them like giant hyperspectral cameras. And the phase space that we're trying to probe is also hypervariate. Hypervariate in the sense that it's more than multivariate, if you like. Multivariate is sort of the bread and butter of analysis for a long time, having many dimensions, but hypervariate in the sense that we're trying to explore phase spaces that are tens, hundreds, thousands, and millions dimensions. And so this is the challenge and the opportunity how to combine these two together. So just to give you kind of a sense, so imagine a collision at the Large Hadron Collider. Typical collision might have thousands of particles. That's the phase space we're trying to probe. Each of those particles has, say, a 4 vector. So that's order many thousands of dimensions. If you add more features like flavor, there's even more. And we try to we detect all these particles that are flying out of our detector with a number of detector components. So say like the Atlas or CMS detectors at the LHC have hundreds of millions of readout channels. And so this is sort of this hyperspectral camera imaging this hypervariate phase space. Okay. And so we've been doing multivariate analysis for many years. But what's new is that the modern machine learning revolution has allowed us to explore these high-dimensional feature spaces in their natural high dimensionality. And so what if the new physics is there, we're just not able to see it because we need our hypervariate vision goggles, which are given to us by deep learning. And this is not just about improving on what we have already. This is about enabling the computational discoveries of the future. What I'm going to talk about today will mostly focus on new technologies enabled with machine learning that were just not possible before. Of course, there are a number of innovative strategies that have allowed us to extend existing approaches, but really I'm focusing here on enabling new approaches. Okay. So here's my roadmap of how we do data analysis in fundamental physics generally. So you have the quote unquote theory pipeline and the experimental pipeline. So, we posit our theory of everything. The ultimate goal is to do inference on what is the theory of everything. And we build giant detectors in order to do this inference. And so we have our experiments given to us from nature, and we have to do some dimensionality reduction and pattern recognition in order to make sense of those data. On the theory side, we have posit some theory, we can simulate it, and then we can do the same data reduction path that we do in data and compare the two to extract information. Most machine learning, I would say, is happening at this stage. And probably when you think of machine learning in the context of physics, probably this is what you think about. Using machine learning as a classifier or regressor in order to improve some particular task to do dimensionality reduction. And I'm basically not going to talk about this much for the rest of this talk, even though there's a lot of exciting work going on in this area in all levels. So at the lowest levels, close to the actual detection apparatus, all the way up to tailored observables for a given analysis and everything in between, calibration, noise mitigation, et cetera. I'm just going to flash a few words on the screen just to give you a little teaser, and I'm happy to talk more about them later, but I'm really not going to focus on them in any detail. So this area also has interesting progress in connecting physics with machine learning in innovative ways. So here's just one buzzword, which is the combination of covariant structures, what machine learning people would call equivariance structures with machine learning. So you could, for instance, imagine constructing a neural network that is Lorentz covariant. You boost the inputs, the output also boosts accordingly. There are also interesting connections between training neural networks or other machine learning algorithms that know about your statistical inference task, so-called uncertainty aware. There are also other connections beyond with the broader applications of machine learning industry, where we need tools to be what machine learning people would call fair and what physics people might call decorrelated. And you could also imagine using machine learning in interesting ways to discover structure of our data. So I'm basically not going to talk about these at all, but I just flash them up here in case anyone afterwards would like to discuss more. Okay, so back to this picture of everything. I want to focus today on three pieces of this pie where machine learning is playing a big and innovative role. So one is called generative models. So generative models are basically simulations. So simulations allow us to produce new data. And so that you can think of as this path. So we have our theory. I want to produce realistic data through a simulation. And I'm going to talk today about how machine learning can be used to augment or accelerate that process. Then there's the inverse direction. So given some data, I want to use my simulation to do inference. And so this is the inverse direction, where we basically want to invert a simulation. Our simulations are often not invertible. And so there's a variety of interesting strategies in order to do inference without actually being able to invert the function. And so I'll talk about that today also. And the last thing I'll talk about is that even though a lot of our work relies on simulation, this is sort of a unique feature at the end of the day about fundamental physics experiments, is that we have ab initio simulations. There are also cases where we think our simulations are either not accurate or we believe that they're limited in their parameter spaces. And so we might want to develop tools that are simulation independent. So I'll talk about that as well. And hopefully this picture will make sense as the talk goes on. Okay, so I'm going to talk about these three core areas at the intersection of machine learning and fundamental physics. Forward models, or generative models or simulations. Inverse models, or doing inference with these simulations. And then simulation-free approaches. Okay, and I'm going to do so by telling you one vignette per area. These are really complicated areas. I could give a whole colloquium just on any one of these areas, but I wanted to give you cover a broad spectrum instead of going deep into any one of these areas. Okay, so I'm going to start with forward models. Okay, so what is a generator? A generator is nothing other than a map from random numbers to structured data. Okay, you can think of like I have a bunch of random numbers and I generate an image. This image is a pixelized image of a hadronic jet. But it doesn't really matter. This could be any structure. And a deep generative model is simply this map where this function here is a neural network or a deep neural network. Okay, and there are a variety of tools to construct this network. One of those, which is particularly clever, not invented by me, is called a GAN, a generative adversarial network. And the way that this network works is actually there's two neural networks. There's a generator function that maps noise to structure, and a second neural network that tries to distinguish examples from the generator into examples from, say, a physics-based simulator. And they compete. When your discriminator, the second neural network, is maximally confused, then you know that your generator is doing a very good job. It's generating examples that look just like the examples from your physics simulator. And so in this way, you can train these two neural networks at the same time. And at the end of the day, you forget about the D network and you just take your G network. And now you have what people in machine learning would call a surrogate model. You have a generator that emulates the physics simulator. Okay. And so this has a lot of implications. And one of the places where it has a lot of potential is in accelerating slow simulations. So once you've trained this model, it's very fast to generate new examples. It doesn't depend at all on the physics. It's because the network itself is sort of the same no matter what energy scale or the complexity of the event. And so one place where simulations are very slow is material interactions. So imagine you have a very high energy particle slamming into some piece of material, say a dense calorimeter. Then you have to march that high energy particle all the way down to ionization energy that you can read out. And so this can be very time consuming. And so calorimeters are often slow to simulate and therefore an excellent testing ground for accelerating methods with machine learning. So here's a picture, which could be like an image from a calorimeter where the pixel intensity, if you like, in this grayscale image is something like the energy deposited in a part of the detector. And you can see here what it might look like in sort of a more three-dimensional view. Okay, so this is great. So GANs could be used as an approximate simulation. They're very fast once I've trained it. And the tools are automated, which enables portability for two reasons. One, if I change my simulation, I can just retrain and I get a new updated simulation. And the other thing is that if I want to generate more examples, all I need to know are the weights of my neural network, which could be a megabyte or something. And I can then from that megabyte generate billions or trillions of examples. Okay. And additionally, we can have control over the physical features of our simulation. So for instance, imagine that I train this generative model conditioned on, in this case, the location where I am inside the detector. And so here, this is an example where if I look at one column, there's a 3-layer calorimeter. Each picture here corresponds to generating one example where I'm conditioning on the location that the particle hits the detector. And I can just sweep through that, but fix all the other random numbers. That's kind of a beautiful feature of these neural networks is that it's just a function. I pipe in random numbers and output comes some examples. So I could fix the random numbers and then just change physical attributes like energy or the location. And you can see, it's easiest to see in this case where like the central blob shifts from top to bottom. Okay, so the kind of first exploration of this was using a GAN called CaloGAN, aptly named. And here you can see the results from a 3-layer calorimeter where we're shooting electrons, photons, and pions at the calorimeter. Geant here is sort of the state-of-the-art simulation tool that's very slow, and the comparison with these 3 different particle types as the energy in the first layer. And it has this kind of these crazy shapes because the pions here, basically they go right through this detector, so they leave comparatively little energy, whereas the photons and electrons are almost stopped by this detector and leave much more energy. Okay, so the time to generate an event is orders of magnitude faster for the GAN than for Geant and doesn't scale with energy. And what's really exciting, so this paper was from 2018, so you might ask, why am I telling you a story about a paper from 2018? In fact, now there have been hundreds of papers on this subject, GANs and other tools. What I'm really excited about, this is a paper from this year actually, or last year, where the Atlas experiment is actually now using a GAN as part of its fast simulation. And it will use that GAN to generate billions of calorimeter showers. And it will be much faster and much higher fidelity than the existing methods. Okay. So where is this going? I would say there's a lot of work ongoing to maintain the speed, the fast speed of these generative models, but improving the precision. And I've only mentioned GANs, but there have now been a number of tools that have been proposed to accelerate simulations that are like GANs but have other features, and I'm happy to talk about that later if you're curious. But there are other attributes we want to embed these neural networks with as well. So the next frontiers I've written here is physics-informed generative models. So generative models that are tailored to the specific structure of our events. So they might have some Lorentz covariance structure. They might have a variable number of outputs. If I imagine like a collision event with a variable number of particles, they might have other structures that encode the physics of the events. And additionally, we need to be able to scale up for next generation experiments. So in this previous example I showed, there's sort of hundreds of calorimeter cells. So that's the size of the feature space. But future detectors might have thousands or tens of thousands of cells, and that's difficult to do with a GAN. We can also imagine embedding these generative models in other parts of the simulation. So the picture that I'm showing on this slide is a prototype for developing a GAN-based model that emulates hadronization, which is the process by which quarks and gluons form bound states hadrons. And there's no first principles understanding of how this works. So we basically just have parametric models that effectively we fit to data. And so wouldn't it be great if instead we use the most flexible parametric models possible, which is a neural network? And this is somewhat complicated because it's embedded in like part of the simulation. So for a detector simulation, it's the end of the simulation stack. But for hadronization, it's sort of in the middle, somewhere between producing the particles and having them interact with our detector. But first look at this. Looks pretty promising. There's data from E plus E minus collisions compared to this is sort of a phenomenological model called the cluster hadronization model, and this is our GAN, which is pretty close. Okay. So that's my whirlwind tour through generative models, just to give you a taste. I'm going to spend a little bit more time in the second and third parts of this talk, which are more closely connected to inference and data analysis. So now I'm going to talk about inverse models, and the example I'm going to give is called unfolding, which in every other area in the world is calls this deconvolution. So I'll explain what I mean by that in a second. Okay, so the ultimate goal is to measure a differential cross section. This is sort of the bread and butter across many areas of particle and nuclear physics. And here's what differential cross section measurement might look like. So imagine you have some observable x, and I want to measure dn dx. This is the differential cross section, the number of, say, events in a given bin of x. Okay, so these are essential because they allow us to compare data with theory with a number of downstream science goals. So if you have a prediction, which maybe has some free parameters, and you want to compare it with the data, this is how you do it. Okay, so current approaches, they use bins. So this is what the differential cross-section measurement looks like. It has a number of bins, and I have a limited number of inputs and outputs, in part because it's binned. Okay, so this is very limiting. And the question is, can we change this paradigm with machine learning? Can I do unfolding, where I have, I don't have to bin, I can have very high dimensions. So this is what I want to do schematically. So I measure some signatures in my detector. So these like lines here are supposed to represent charged particle trajectories inside a magnetic field, and these blobs are supposed to represent energy deposits inside a calorimeter. So I measure this high-dimensional feature space, and I would like to infer something about the hadrons that hit the detector. So this is like kind of removing detector distortions. Okay, so if I knew the likelihood, the probability of the measured given the true, this is measured, this is true, I could just say, well, my unfolded value is simply the maximum likelihood estimate. I just say, okay, I'm going to take my result is just going to make the true that maximizes this likelihood. Okay, and I would just be done. That would be great. But the challenge is that I already mentioned the measured data are hyperspectral. The true spectra are hypervariate. So I definitely cannot write down P of measured given true, the likelihood. So if I can't write down the likelihood, how am I supposed to possibly do maximum likelihood estimation? And the answer is that even though we can't write down P of measured given true, I can sample from P of measured given true. This is the whole point of a simulator. So I can simulate, I can run what people in machine learning call the forward model. And so there's a whole area of machine learning, basically at the intersection of machine learning and physics, called likelihood-free inference. So I want to be able to do something like maximum likelihood estimation without ever being able to write down the likelihood, which might sound impossible, but now let me give you a sense of how this can be done. Okay, so we've introduced a new machine learning method, which is unbinned and high dimensional, which allows us to do exactly this. And I think this will really dramatically change how we do cross-section measurements, because we don't have to bin, we don't have to pick the observables ahead of time even. We can do a high-dimensional unbinned cross-section measurement, which would be unheard of. Okay, so we call this method OmniFold, and I'm going to briefly describe it schematically, but I'm very happy to discuss the technical details later. So here's a picture where the top row corresponds to nature, and the bottom row corresponds to some synthetic simulations. The word simulation here is a bit overloaded, so I'll try to call this synthetic in this nature. So the ultimate goal is to infer the particle level nature, the hadrons that would have hit our detector without any distortions from the detector. And we measure signatures in our detector. So this picture here shows a transverse cross-section of the Alice detector, where the protons are coming into and out of the page, and you have these particles flying out in all directions. You can see there's sort of two sprays of particles that correspond to two jets. And so I want to look in this image and extract the information about those jets, for instance. Okay, and I'm aided in this quest with a simulation. And the key feature of the simulation is that for every event, I know the right-hand side and the left-hand side, because I simulated it. I can have a particle level event, and I know what it looks like if I pass it through the detector. And this map going from here to here, right to left, is stochastic, because my detector noise is stochastic. Okay, so it's not invertible. All right, so this procedure, this OmniFold procedure, which I'm now going to describe, is called an expectation maximization algorithm. So you've taken statistics class, you may have heard of that algorithm. Basically what it does is it iteratively achieves the maximum likelihood estimator without at any point ever writing down the likelihood. And in this case, it does it by using likelihood ratios, which is the magic that machine learning is going to solve here. Okay, so the first step in this procedure is that we take the data of the simulation at detector level, and we learn a reweighting function from the simulation to the data. So we learn importance weights to make the simulation look just like the data at detector level. And the magic that allows us to work is that we use a fact that machine learning classifiers are learning secretly likelihood ratios. It turns out that if you want to distinguish between two different samples, the best way to do that is to learn a likelihood ratio. So classifiers are likelihood ratio estimators. Okay, and so this allows us to do this naturally high dimensional and unbinned because classifiers, our neural networks, are very naturally unbinned, and they can easily accommodate high dimensional structure. Okay, and so now I have these weights in my simulation that basically allow the simulation to match the data. And you might ask, well, am I done? That is at the end of the story. And the answer is no, because what I really want at the end of the day is I want my simulation at particle level to have weights that I can then use to make any spectra that I might see in the detector. And the reason I can't just use those weights that I learned at detector level is because the map from particle level to detector level is stochastic. So you can have one phase space point at particle level, which gets mapped to multiple phase space points at detector level. They all get different weights. And then what do? Which one do I pick? And so there's a second step, which you can think of basically as taking the local average. So for a given phase space point, we train another neural network that locally takes the average over all the points weighted by their probability at detector level. And then you can rinse and repeat this procedure. Okay, so there's two neural networks, this one, and it's iterated a number of times. And we can accommodate the structure of the events by using state-of-the-art classification neural networks in order to do this. So it changes the problem of density estimation, learning the likelihood, which is hard, into the problem of classification, which is much easier. Okay, so that's the magic. And here is proton-proton collisions, but okay, it could be anything. So here's proton-proton. This is actually a picture of electron-proton collisions, which looks about the same. I have simulations going from electron-proton. Here you can see an electron. Here's a jet. It's very similar to this picture. Okay, I just swapped out one of the electrons for a jet. And there are simulations which allow us to go back and forth. And why stop there? I can also imagine DIS with neutrino experiments. Say I have a neutrino beam, which is incident on some matter, and I scatter, say, another lepton, and I want to see what happens. So here's a picture, for instance, of such an event display from the T2K experiment. And once again, I have my simulations, and I can go back and forth. So this structure is very common across particle and nuclear physics, and we can imagine applying this technique to a number of different areas. Okay, so we have, at least we've started to do so. So we've already been delivering science results with this methodology, and more are on the way. Personally, I'm collaborating with Jing, who's in the audience, and she can tell you all about it. But I know there are a number of other people here who are exploring the use of these techniques. I'm really excited to see what it will look like for the next generation. Let me just explain each of these one at a time. They correspond to the different examples I just told you about. So here's one from an experiment called H1. Probably many of you in the room were born after the H1 experiment was created. So just a reminder to everyone, H1 was an experiment at the Hera Collider, which collided electrons and protons at DAISY in the 90s to the mid 2000s. You might ask, like, why am I talking about Hera right now? And the answer is because electron-proton collisions at Hera were sort of unique. We haven't had such a collider so far, although we're going to have one at Brookhaven in the near future. And these data are really precious. And they were never analyzed in the guise of modern jet substructure, modern jet physics, modern machine learning. And so it's a treasure trove that we're now reanalyzing. And so this particular measurement that came out last year is looking at electron jet correlations in the lab frame. And it's really a very interesting observable. This one here, this QT is the momentum imbalance between the electron and the jet. So at leading order, if all you had was just the electron and the jet, you'd have them be back to back. And so the momentum imbalance would be 0. You'd be like, infinitely far to the left here. And there's a little bit of a kick for 2 reasons. One is that you get some radiation off of the quark. And the other reason is that the initial quark had some momentum imbalance. So it wasn't just going collinear with the beam. And so these 2 regimes, the hard radiation off of the quark and the initial imbalance, are sort of these different regimes that we can now probe holistically. And this measurement actually was done unbinned in 8 dimensions. I'm showing it as a histogram here because I have to be able to see it somehow. But this was the first unbinned differential cross-section measurement using machine learning with legacy data. So it's really combining a lot of exciting subjects all in one go. And I think we just had a press release about this actually this last week. And I think the science writer at Berekley Lab said it really well. How do you solve the problem like the proton? You smash it to smithereens, then build it back together with machine learning. That's exactly what we're trying to do. And all the credit goes to my postdoc, Vinny, who's amazing. Okay. But as I said, we can apply this strategy to other collision systems. So why stop at electron-proton? Here is an example where we're applying it to E plus E minus data. Now we haven't had an E plus E minus collider even longer. It was even longer ago than Hera. So these data in this plot were taken in Aleph. These data are from 1996. But once again, many of you in the room maybe weren't even around then. I was barely around then. But these data are also quite precious, and we're now studying them. And in this context, we're looking at an observable called the thrust, which basically measures how uniformly distributed the particles are inside an event. When thrust is close to 0, they're very pencil-like back-to-back jets. And as thrust gets larger, it's sort of more uniformly distributed. And this observable is very interesting for a number of reasons. But in the context of OmniFold, it's very interesting because there are certain parts of the distribution, namely this region over here, where you'd like it to be log scale, because you want to be able to measure, say, the strong coupling constant. But other parts of the distribution, you want to probe different kinds of physics. But this measurement was done only in linear bins. And once you've done the measurement in linear bins, you're stuck. You can't easily rebin. But OmniFold is unbinned. So it's trivial. It's 1 line of Python code for us to go from one kind of binning to another kind of binning. And so everyone can basically be able to use the data as they like by going from different bins. And so we hope that we can explore these data in more detail. And actually, there's kind of a long-standing tension in the extraction of the strong coupling constant between E plus E minus and lattice methods. And it's a non-trivial tension. It's actually 3 sigma. You probably haven't heard a lot about it because I think no one thinks this is new physics, but it's still sort of a problem with our understanding at a deep level that we'd like to understand better. Okay. And the last example I'll give for this unfolding is a totally different collision system, now fixed target. So as I mentioned, this is neutrino experiments in T2K. And here is a very early study looking at the spectrum of the muon momentum unfolded in these collisions, which include a number. It's lower energies. You can see here that's 2 GeV. So at high energy, it's DIS, and at lower energies, there's a number of different processes that contribute. And this is a very fun stress test of OmniFold because the T2K detector is very inhomogeneous. I don't have a picture here, but there's a number of different systems. And so the detector responds very strongly as a function of where you are in the detector. And with OmniFold, it's very easy to add position. So you can simultaneously unfold, say, the energy spectrum with the position inside the detector, whereas traditionally this is very hard to do because imagine you have to make a matrix, a binned response matrix. And you want that matrix to be conditioned on a bunch of different observables. You have to basically parameterize a matrix. Whereas here, there's no such thing, which makes it very effective. Okay, so where is this going? I would say one thing I'm really excited about for the future in the optimal combination of simulations and machine learning is differentiable simulation. So far, I've been talking about using surrogate models. So basically, I trained a classifier to reweight my data to match my simulation to match my data. But imagine that my simulation itself was a neural network. Then I wouldn't have to learn this reweighting procedure. I could just take my simulation and just move it around. And that would really unify the simulation and the inference and has a lot of other nice properties. So I basically don't have time to tell you what exactly I mean by that, but let me just show you one picture. So this is a picture where we have a simulation for E plus E minus collision. So E plus E minus goes to hadrons. And there are two events, a red event and a blue event. And these are the spherical coordinates. So imagine I have my detector, it's like a sphere. And so there's the polar angle and the azimuthal angle, and the size of the blob corresponds to the energy deposited, okay? And there's basically one free parameter in these collisions, and that's the strong coupling constant. And so what we're doing here is we've written the simulation differentially. So basically I can take a derivative through the simulation, and I can basically tailor expand the simulation. And that may sound like science fiction. And in some sense, it's really magical that we can do this. And I'm happy to explain more later what exactly that means. But basically what you're seeing with these different blobs is where it's the Taylor expansion of a single event. So you have a single event, and I'm asking event plus derivative of event times delta strong coupling constant. And as we sweep the strong coupling constant, you see the blobs move. That basically corresponds to how the simulation responds, the particle event would respond to changes in the parameter of interest. And so in this way, the simulation itself is sort of like a neural network. I can take gradients, I can even make it part of another neural network, and this enables a new kind of inference in the future. Okay, so now my last part of my talk will be about simulation-free methods, and the example I'm going to give is anomaly detection. Okay, so nearly all searches for new particles are signal model driven. We start by looking at an event like this, imagining what some kind of new physics might look like, and we say, okay, I'm going to look for supersymmetry. So I know the particular model I'm going to look for, and I'm going to imagine coming up with some observables to look for this kind of physics. So I'm going to take jets, and I'm going to compose some simple combinations of these jets in order to construct observables that will allow me to look for this particular model of new physics. Now, anomaly detection is sort of a model agnostic program where we sort of throw out this and we say instead, let's not anchor ourselves in supersymmetry. Let's be more open-minded about what the new physics could look like. And let's say, well, let's just think of a final state and ask what could be there? What's the question mark? And anomaly detection in fundamental physics is inherently different than anomaly detection in science, in other areas of science and industry, because we're at the point in our field where I can't look at a single event and say, this is new physics, Nobel Prize for you. Instead, we're at a stage where we're only in context can you tell there's something new. The example I like to give is, it's not like flying elephants. If you saw a flying elephant, you would know there's something crazy, but instead, there might be a few more elephants than usual at the local watering hole, which requires you to know what is the distribution of elephants at the watering hole, and then to see if there's something anomalous happening statistically. Okay. There are a number of proposals for doing anomaly detection with machine learning, and I like to categorize the different methods based on what the physics assumption is that they're making. And they can be categorized based on what's called supervision. So supervised learning is sort of mostly all machine learning that you know about. You have full label information. So if I want to train a classifier to distinguish cats from dogs, I'm going to present my neural network or my other whatever machine learning method with a bunch of pictures of cats, a bunch of pictures of dogs, and I tell it which are cats and which are dogs. And then it looks at those pictures and then it tries to, in the future say, this picture is a cat or a dog. But we don't want to assume a model of cats and dogs. We want to be more model agnostic. And so we have to use less than supervised methods, and they have different names: unsupervised, weakly supervised, and semi-supervised. And now I'm going to go through these each one at a time. Okay, so unsupervised learning means there's no labels. I'm going to train a model to do some task without telling it which is signal and which is background. And the general strategy of these approaches is to learn either explicitly or implicitly the density of the data, the probability density. And the goal is to look for events that are quote unquote rare. And so if you learn the density, you can then say, oh, I want events that are rare, so low density. And one strategy for doing that is called an autoencoder. So an autoencoder basically learns to compress and then uncompress the data. So it learns two models, an encoder and a decoder. So you imagine taking some input data, encoding it, and then decoding it. And this is trained by requiring that the encoded, decoded data are very similar to the original image. And so in that way, you can see it's unsupervised. I'm not telling it which data are signal and background. I'm just telling it to compress and uncompress with high fidelity. And the point is that if it's doing its job, it should allocate more capacity to common events, and it should allocate less capacity to rare events. So when you pass a rare event to the encoder and the decoder, it should do a very bad job of reconstructing the event. And so one way of doing anomaly detection is to take events, pass them through, and ask if they look very different than the original event. Whereas if you had an event that you pass it through and it looks very similar to the original event, you might say, well, that's probably a more common kind of example. Okay. So then there's weakly supervised. And here you have labels for every example, but they're noisy. Okay, so what does that mean? In practice, it means you have two data sets, one that's signal enriched and one that's signal depleted. I don't actually know for any individual example if it's signal or background, but I know that one of my data sets has more signal if the signal exists. And so then you try to learn likelihood ratios. So the signal enriched over signal depleted. And in that way, I can ask for events that are more likely to be signal than background, which might sound like a very similar question to asking for rare events, but it's actually totally different. Because asking if it's rare only requires one sample, whereas asking if it's more signal-like compared to another sample requires two. Okay. And the third thing is semi-supervised. And here you have partial labels. So for some examples, you have labels and some you don't. And typically these methods, they operate by training, say, a classifier to distinguish data from some concoction of signal models. So here's like, the whole standard model and all of its glory, trained to distinguish between, say, a bunch of different signal models. And the assumption is that the new signals that you're looking for are more like signals that you know about than the background. And so in that way, you can be sensitive to other signals that you didn't train with. I'm not going to spend any time talking about this for the rest of the talk. So now let me just summarize. We have unsupervised, no labels, weakly supervised, noisy labels. And so the assumption of the physics is that unsupervised methods assume that the new physics is rare, low density, whereas the weakly supervised assume that the signal is an overdensity, so high likelihood ratio. Now, the main drawback is that rare is not coordinate invariant. So if I change to a different coordinate system, the likelihood, the density changes by a Jacobian factor. And so this depends on what you mean by rare, or what your coordinate system is. Whereas likelihood ratios, they're independent, they're invariant under coordinate transformations, but they require having two samples. Okay. So I'm going to give, in the last minutes, an explicit example in this case. And the canonical example is a resonance search. So I'll say what I mean by that in a second. So a very general strategy is to imagine there's some dimension, some observable called mres, a resonant feature. I use m because it's often a mass. And for this observable, the standard model background is just some smooth featureless distribution. It could be steeply falling, but it doesn't really matter. And the signal, if it exists, is going to be localized somewhere. I don't know where it's localized, but it's localized somewhere. So this is generically true if I have some new particle that's produced on shell. The mass, the reconstructed mass will be the resonant feature, and the standard model background will be the continuum. Okay, so the first thing I need to do, let's say if I want to do weakly supervised learning, is generate noisy labels. So I'll do that by making a signal region and a sideband region. And so then I can generate my noisy labels. I can say signal region, noisy label of 1, signal, sideband region, noisy label of 0, background. And then once I have these labels, I can use whatever other dimensions I have available in my data to train my classifier in a weakly supervised way. So it has these labels which are not quite correct, but I can still use that to find some anomalous features in the data. And I've drawn it here as a one-dimensional feature, but in principle, this could be, a few, 10, 100, 1,000 dimensions. Okay, and so as an explicit example, here's my dijet example again. As a reminder, here's a cross-section of the Atlas detector where the protons are coming into and out of the page and out go the collision debris. Here are two jets. The invariant mass of the two jets could be the resonant feature. If I had a new particle decaying into jets, that would be the mass of the particle. But in the strong force just happily will give you a falling spectrum of mass. And I could look inside the jets at the jet substructure to look for something new. So this way I could look for anomalous jet substructure and then see if there's a bump on top of this steeply falling background. But I don't have to just look in proton-proton collisions. I could look at, say, E plus E minus collisions. And here's a very similar setup where, let's say I'm looking for, once again, a dijet resonance, but instead of hunting in the invariant mass of the two jets, I could be hunting in the square root of S, the center of mass energy, by looking for, say, like a radiated photon. And then I could look at the center of mass energy, and I can basically scan the center of mass energy by looking for radiated photons. And then I can look at the structure of the event to look for something new. But why stop there? I could look up to the sky, and I could imagine, once again, looking at some other structures. So say I want to look for objects like cold stellar streams. These are proto-galaxies that have been ripped apart by the gravitational potential of the Milky Way. And the thing is, because they're all from the same proto-galaxy, they are co-moving with the same velocity. And so if you like, these streams will be resonant in proper motion. And I can use other features of these streams to look for for anomalous differences between the stream and, say, the Milky Way stars. And so here are three totally different examples where I can apply the same methodology to look for new physics. Okay, and we've done that, at least we started to do so. So this program is really just getting started. There are many challenges to scale up, but early studies are really quite exciting. So here we're applying basically the same method in three totally different systems. These are both collision systems, and this is astrophysical. Okay, so this one is a recent result from the ALICE detector, where we basically done exactly the search I just described, where you use this weakly supervised approach, and we're using the jet substructure in order to look for something anomalous. And this picture shows the mass of the two jets. These are jet substructure properties, and this is in some particular bin of invariant mass, and we've injected a signal into the data stream to show that we can find an anomaly if it was there. And we injected a signal at that cross, and you can see the orange there is the data. So we trained a neural network on data. We didn't tell anything about where the signal was, and we injected a signal and it found it, which gives us confidence that it could find something new. Unfortunately, we didn't yet find anything new, but we're hopeful that in future rounds it will find something. In E plus E minus, we've studied this in simulation, where we can explore, in this case, this is the center of mass energy with these radiated photons, and we can look at the presence of different potential anomalies, and using all the particles inside these events in order to reconstruct potential signals. And this may have important implications for the design of future detectors, where we can imagine a more model agnostic physics program. And lastly, I described these cold stellar streams, where we can use potentially weakly supervised methods to automatically scan for the presence of new streams. And here is a picture that shows in the coordinates on the sky a particular stream called GD1, and we've automatically identified the presence of this stream and verified it against a known catalog using this approach. Okay, so where is this going? I think the idea here is we have a bunch of strategies which we need to scale up, but we're ready to now deploy them to different data sets and interpret what they mean. And we need to push the dimensionality. So far, all the examples I've shown are low dimensional, so order 1, so a few dimensions. But we want to be able to go to higher dimensions and also relax some of the assumptions. So for instance, that we have a resonance. Okay, so this is a picture that shows the sensitivity of these methods. This is this proton-proton goes to dijets. And if we inject a signal, basically this is automatically able to identify there's something weird in the data. This is the p-value, so low p-value means there's something weird. Okay, so that basically brings me to the end of everything I wanted to say today. I covered a lot of territory very quickly, but I hope I was able to convince you that at least in these three broad areas, forward simulation, inverse simulation, and anomalies, and simulation-free methods, that machine learning is really allowing us to do new and exciting science that we couldn't do before. And this is only the start of an exciting path with modern machine learning for this intersection of machine learning and physics. And we really need innovative computational techniques in order to enable the data-driven discoveries of the future. We've looked in many places using traditional methods, and we should continue to do so. But it's essential that in order to make the best use of our data, to examine them holistically using these machine learning methods. It's not just about achieving precision and proving what we've done before. We should do that. This is really enabling new science. And I added in bold here, we need physicists. So I'm a physicist doing machine learning, and this is really essential because we have unique challenges that require dedicated and unique solutions. All right, thank you. And this is a picture of my group, and for some reason I have many Yale people who keep ending up in my group. I don't know why.
Okay. Yeah, so thanks for the very nice talk. So are there any questions for Ben?
Thanks for your talk. I just want to know, is there any limitations on what type of theory you can apply machine learning to? Yeah, that's my question.
Yeah, so perhaps you're asking in the context of anomaly detection. And I would say in the resonant case, I basically know what to do. There's like a program that's like clearly can be improved and expanded. In the non-resonant case, I don't know what to do in general. There are a number of specific cases where I have some strategies, or other people have come up with some strategies. But the general case is wide open, I would say. And we have to just tailor, we need a number of methods that are tailored to specific, general cases.
So maybe we can go with the question on Zoom from Tong.
Yeah, thanks, Ben, very nice talk. So I actually have a question about like the rare signal you were talking about in the last part of your talk. So we know some new physics will lead to the rare signal that you were talking about, but there are also possibilities, especially like in detectors that, some detector anomaly, for example, the ADC just gone wild versus the TPC has some problem, whatever, that will also lead to some quote unquote rare signals. So do you have a way to just distinguish between these, or is there where some human intervention needs to come in and actually decide, okay, this is just a detector anomaly versus, okay, that's a new physics? Thank you.
That's a great question. Yeah. So in general, depending on how you set up the problem, you might find problems with your detector, which I would say is also a success. Sort of depends how you're looking at it, but indeed, in some cases, these methods will just find problems with the detector, and then additional diagnostic tools are required. But in other cases, these approaches can be robust to detector problems. It just kind of depends what your detector problems look like. So for instance, in the resonant case, it's often hard for a detector problem to be resonant. Many things have to conspire. It can happen, but it's rare. And in this case of looking for things that are rare, indeed, people have proposed using autoencoders and other approaches for data quality control, for instance, which I think is a great use case.
Any other questions for Ben?
Okay.
Hey, great talk. So as a high energy physicist, you well know, we're often in the business of not finding things. But we make lemonade, and you can set limits on a theory and do exclusions. So in the context of anomaly detection, to what extent, I mean, obviously when you have no model, it's not a well-formed question to say, what did you learn from this when you have a null result? But to what extent can you convert, say, a null result from anomaly detection into some theoretical kind of lesson?
This is a great question. In general, because these methods are probing very large feature spaces, it's hard to quantify what you didn't find. And so the way we try to do this, I don't have the slide on my backup, unfortunately, is we inject particular signal models that sort of probe the boundary of where we think we would be sensitive. Now, of course, that's a huge space, so I can't do it exhaustively. But by kind of probing, a little bit in different directions, we can kind of see how big is the balloon that we're actually sensitive to. And that's the strategy we've taken so far. But this is interpreting these results is definitely an open question, and reinterpreting them is an even more open question. So in traditional searches, right, I can say this is my event selection. You as a theorist can ask, what would my prediction for a particular model be if I pass it through your event selection? But these approaches, the event selection depends on the data. So if you had signal in the data, your event selection would be different. So they're not recastable in the traditional sense. And so we need a new strategy that allows us to, retrain neural networks on the fly in order to get to these results. So in particular, for this, setting limits on this particular model, we had to train something like 10,000 neural networks. Why? Because for every different signal model, for every cross section, you have to retrain the neural network, which is a big pain. Yeah.
Hi,
Hi.
Excellent talk. Slide 57, you show a distribution, I think it's from T2K. And I find it very impressive that your algorithm matches the data better. And you probably mentioned this, but why is the reason that the simulation or simulation does worse than the algorithm with the simulation?
Great. Yeah, it's misleading in this plot. So everything in this plot is simulation. And basically, so I'm not a member of the T2K experiment, so I don't have access to the data, but I convinced my T2K friends to make their simulation public. And so this is all in simulation. The data here is basically one systematic uncertainty, and the simulation is a different systematic uncertainty. And they're pretty close to start with. But you're right that in actual neutrino experiments, the data and simulations are often very different, which is one of the main goals of this approach, is that we hope to be more simulation independent by using more data, more dimensions to do the unfolding. Yeah.
I also had a question about the likelihood-free inference methods and using simulation, which is, yeah, do those methods have a closer analogy to frequentist or Bayesian statistics? I mean, I know that those methods of statistics have different assumptions baked into what it means to do a measurement. But, you know, I wonder if can you incorporate priors here? What sort of statistical principles does this correspond to, or is it sort of its own thing separate from Bayesian or frequentist inference?
Yes. So this, as I've described it, this achieves the maximum likelihood estimator, which is a frequentist approach. But so you can think of it like it's a frequentist approach, or if you like, a Bayesian approach with a flat prior. And so it's by obligation, I'm a frequentist. But in principle, this method could be modified to do Bayesian analysis. Yeah. In fact, it'll be fun to think about. Yeah.
So I have a more general question. As someone who just started appreciating the broad literature of machine learning, like from the literature of statistics and computer science and information theory, all combined, like giving rise to, and also thanks to the rising computational resources, to the rising field of machine learning, and then most excitingly, help us do like better detector design and better or qualitative new ways to do physical analysis. So one thing I always found incredible when working with you is like you seem to always have an incredible amount of new ideas. So I'm just curious, like whether they're more like physics driven, like more come from some physical problem in the analysis that you want to solve, or more from the literature of the other like different fields that they have like new derivation, for instance. And
I would say it goes both ways. Yeah. So in some cases, there's a problem I want to solve. In this case, unfolding. I draw from, I develop new tools in order to solve it. But there's some cases where there's a shiny new tool, and we just want to see how it works. So for instance, I think I have one slide in the backup about. So I talked about GANs, and GANs are by now old news when it comes to generative models. But so there's GANs, but there's like other methods, and these methods called diffusion models are like the latest and greatest. They're like if you look at like the top rated image recognition, image generation, they're all diffusion models. And so I learned about that, and so we tried testing it, and it works really well. But that's sort of like driven the other direction. So it goes. I think it's important to go both ways. We have to pay attention to what's going on in machine learning, but we also need to tailor methods for our particular problems.
To what extent do these modeling include insights from generalized probability, or is it purely probability theory and frequentist methods and Bayesian? Yeah,
so I mean, ultimately, we want to do like the standard kind of inference that people are doing now. Like the question asked earlier, like how do we compare to do standard statistical analysis? So in the anomaly detection, I need to be able to find a strategy that allows me to compute like frequentist p-values. In order to compare with like traditional approaches, or in the case of unfolding, like classical frequentist maximum likelihood estimation. But it's possible that we can maybe extend these frameworks, and I'm really excited to think about that. So in the case of so both of these problems, unfolding and anomaly detection, are what statisticians would call ill-posed problems. There's not like a unique solution. In the anomaly case, because there's like an infinite number of possible anomalies. And in the deconvolution case, it's because the map is not invertible. And so it's actually fantastic to think about what are the statistical implications of that when I start doing things in high dimensions. Yeah, so there's a lot of interesting foundational statistical questions to think about as well. Yeah.
Yeah, if you could forgive me a very broad question here. What's the limiting factor in this research typically right now? Is it like GPU hardware, architecture, resources, et cetera?
Right now, I'm not limited by GPUs. So I'm really excited to say that at Berekley Lab, we have a brand new supercomputer called Perlmutter, named after a high energy physicist or cosmologist, Saul Perlmutter. And I have 10,000 A100s at my my fingertips. So I'm absolutely not limited by hardware. So for sure, my idea is limited right now. Yeah. I mean, of course, scaling up is a challenge, but not the availability of hardware. Yeah. So we really need new methods and also technical innovation to scale up.
Well, hi, this might be a little rudimentary, but how do you, when you're talking about the GAN simulations versus traditional methods, how do you quantify the fidelity of these? Or is it just the fact that it's significantly faster and seems to recapitulate results sufficient for implementing for future work?
It's actually a great question because we're generating these high dimensional spaces. How do I know it's good? If it was a one-dimensional thing, I could look at a histogram and compare by eye. But if I'm generating like a 1,000-dimensional space, I can't visualize it that. Well, I can't, maybe you can, but I think, and so really we need to develop new diagnostic tests. So one thing you can do, which is very powerful, is imagine you train a classifier, a post hoc classifier, to distinguish my generated data from my actual data. And if it's like very difficult to compare, to distinguish them in my high dimensional space, then it's doing a good job. But that's a really hard test to pass, actually, because you have to be really good. But the latest models are sort of starting to achieve that performance. Now, being able to interpret exactly what goes wrong, like where are the defects, is a really hard question. I would say is open R&D.
So when you develop cutting edge methods like these, which can have applications across subsystems, across experiments, even across fields, what's the outreach pipeline like for like making sure your methods are actually like adopted? Yeah, that's also a huge challenge. Even within experiments, there's like huge sociological problems. I mean, getting this analysis through the Alice experiment was, it took a lot of sociological, willpower. I would say, I mean, all the examples I showed today, these are works that I'm personally invested in, like people in my group are working on. So one way of getting things through is, doing it yourself. But I also know that there are people in the audience who I'm not working with directly, who are implementing some of these methods. And I'm really excited about that. And I think really, at the end of the day, if we can show you can do new things that are useful, hopefully then, we can convince our collaborators and colleagues that these are tools that are really useful. And in addition to, one thing that's also important is that making software available. So we work pretty hard to have public software that people can use to reproduce the results that we've made, and also to make it easier for other people to try it, trying things out.
So thanks for the nice talk. So I was wondering for the OmniFold method, for like either in E plus E minus or electron proton collisions, are there any like tests to see if prior dependence of OmniFold is greater or less than the traditional unfolding methods?
Yeah, I don't have a plot in backup, but we have done many tests to show that the sensitivity to like changing the prior, if you like, is lower the more information you put in, which kind of makes sense. If you think about it, like if your response matrix is diagonal, then there's no dependence on the prior. And the more dimensions you add, the effective response matrix becomes diagonal in the high dimensional space. And so we've done a series of tests where like we add or move information. We showed the more information you add to the unfolding, the less you're sensitive to your starting point. So yeah, definitely it's the case.
Okay, so I think for time, maybe we'll try and wrap things up now. And let's thank Ben again for the great talk.
Thank you.
I'm sure he'd be happy to take more questions after.